right, good afternoon, chemists. We're going to jump right into it so we can finish this chapter because chapters 4 through 6 will be on the midterm next week. Most of you have your midterm on Tuesday evening, yeah. So do make sure if you're SLDS or if you have a conflict, if there's a conflict, do fill out a makeup request form for the midterm. If you're SLDS, do make sure that you schedule your own midterm within the 3-day window. Okay. All right, so we left off talking about electrons behaving both like a particle and a wave. And so de Broglie was the first one to really propose this new idea that electrons can be waves, even though they are, in fact, particles. We calculated the de Broglie wavelength of an electron. Moving at a certain speed, we see that its wavelength is in the angstrom realm. And so Heisenberg took this one step even further and applied the idea that these electrons, because they're very, very small, what happens is that we can't know their certainty in either their position or velocity we can't know both of them at the same time, essentially. And so we used Heisenberg's uncertainty principle to calculate the minimum amount of uncertainty in an electron's position using this equation, where uncertainty in the velocity just comes from this plus or minus portion. So the actual velocity doesn't actually matter. It's the uncertainty in the velocity that matters. So we see it's 0.05 times 10 to the 6 meters per second. That's the uncertainty. Together with the mass of the electron, we calculated the minimum amount of uncertainty is about a nanometer. So, that's on an atomic scale. So there's a lot of uncertainty required for an electron that's on the scale of that size of an atom. So that's where our orbital shapes will come into play. And so the idea that electrons are hard to find, right? Either their position is poorly defined or the velocity is poorly defined. That's the whole idea between, that explains, you ever hear about like Schrodinger's cat? Yeah, that's like a thing that like you see on the internet, cute little cat. It's both dead and alive at the same time. So I just want to explain where this kind of term has come from. So Heisenberg actually came up with this thought experiment, and it all has to do with the uncertainty related to an electron, right? An electron is hard to find. Just like if, this is just a thought experiment, if you put a cat in a box with poison in it, and you close the box. If the box is closed, you don't know if the cat took the poison and died, or if it didn't take the poison and die. One of those two scenarios is going to be true, right? So when the box is closed, the cat is both dead and alive at the same time, because you don't know whether the cat has taken the poison or not, right? So it has to be both. And so we also call this quantum superposition, meaning that the cat possesses both those properties, dead and alive, at the same time, until you open the box. Once you open the box, that's what it would be like taking a measurement of something. So you're collapsing the wave function, and what you do is isolate. You know for certain that the cat is dead or alive at that point once you open the box. But the point of that whole thought experiment is that when the box is closed, the cat has to be both dead and alive. It has quantum superposition at that point until you open the box and actually take the measurement. And so like the whole idea of like things get really weird when they're small, the whole quantum realm and everything. So I watched Ant-Man and the Wasp like a couple weeks ago, and I added those pictures to these slides, and I was just thinking about it so Ant-Man and the Wasp, that was like the second movie of Ant-Man. Yeah, anyone watch it? You watch it, Ant-Man? Yeah, okay. And so like the whole antagonist in that movie, if you remember that movie, it was like the really shifty girl. Like she would shift through like her atoms were basically hard to find. They were in two places at once. So really the whole antagonist of that movie, the shifty girl, was, she's basically the embodiment of quantum superposition, where she's kind of two places at once. And that's kind of amplified by the idea of things get really weird when they're small, like in the quantum realm in that movie. So hopefully that clarifies where the whole cat being dead and alive thing in a box comes from. It's quantum superposition. So you can impress your friends when they talk about that. All right, so so now we've added this idea of uncertainty in electrons, okay? So if you ever took chemistry before, I feel like most folks learned about s, p, and d orbitals and the shapes, okay? So the idea that electrons can reside in this certain space, right? Like in an s orbital, they're going to be found in this sphere. In a p orbital, they'll be found in this dumbbell shape. That is how we utilize this uncertainty in position, because we talk about electrons not knowing their exact location, but instead saying, hey, you're going to find an electron in this approximate location. And that's how we utilize the uncertainty principle. All right, and so I'll show you the historical steps that we got from Heisenberg's uncertainty principle to our orbital shapes, and it requires a new type of mathematics to do that, which is called quantum mechanics. So Erwin Schrödinger took the ideas that electrons are both particles and waves, took the idea of Heisenberg's uncertainty principle, used a new type of mathematics, quantum mechanics, to solve for where will you find an electron on this atom. So this is the Schrödinger equation, all right? Where obviously I don't want you to memorize this equation. The equation is not important. What is important is the solutions that come out of the equation. But I just want to show you the math steps to take, how we got quantum numbers, all right? That there was very, very advanced math to get there. So we have this equation where we have upside down triangles and pitchforks in them. If you take higher level math, you might do something like this. But what I want to show you is that this equation solves for the electron on a hydrogen atom by looking at its total energy. So if we recall from chapter 5, we talked about internal energy of systems before in a classical manner, where the internal energy of your system is the sum of all of the kinetic energy and all of the potential energy. So let's take a closer look at the Schrödinger equation, all right? So if we look at this first term, where it has this mass term and how the wave function moves from one point to another, doesn't this term kind of sound like kinetic energy, right? Kinetic energy is mass velocity squared, right? So it's taking this mass factor and velocity factor, putting that together. So this term kind of sounds like kinetic energy, doesn't it? And let's look at the term we're adding it to. So this term in our Schrödinger equation describes the forces acting on a particle. What does that sound like? Forces. Potential energy, yeah. So really the Schrödinger equation is just another way to talk about the classical internal energy is kinetic plus potential at the same time, where we have kinetic energy plus potential energy equals the solution to the total energy of our electron. Right? So it's not that different. It's not that different. It's just a new type of math to do that. Right? And so what comes out of the Schrödinger equation is the 100% solution to our hydrogen atom problem that we've been having. Right? We want a model to correctly represent the energy levels of a hydrogen atom that match what we see experimentally when we do a line spectrum experiment. And so that's what happens with our Schrödinger equation. Once we have that, we solve for the energy levels of our hydrogen atom. We see that the lines that come from this computer-generated Schrödinger model match exactly what we see in a line spectrum for a hydrogen atom. So the Schrödinger equation 100% correctly predicts the energy levels of our hydrogen atom, even better than what Bohr did. Bohr, he got it like 95% correct, but Schrödinger took it to the next level and made it 100% correct. But I will point out that the Bohr model is just fine to predict most things. And so the main differences between the Bohr model and the Schrödinger model is that the Bohr model actually violates the uncertainty principle. Violates uncertainty principle, all right? Because the Bohr model just said, oh, you have like an electron orbiting a nucleus at a defined distance away from it. So that's a very small uncertainty in position. So Bohr's model actually violated the uncertainty principle, but the energy levels were very, very close to what we determined experimentally. But the Schrodinger model then introduces the idea of uncertainty, makes these orbital shapes, and it does not violate the uncertainty principle, all right, because those shapes have a very, very large uncertainty within there. Right, so we'll talk about the solution to the Schrodinger equation. So this is just the Schrodinger equation, all right? But then you actually have to solve it, all right? And so you solve it using polar coordinates, actually, all right? And so the solution to the Schrodinger equation looks like this. And so if you take higher level chemistry or higher level math, it's like a rite of passage to solve the Schrodinger equation once. All right, but then we never do it again because we have supercomputers that do it for us because it's very tedious. But what's important here is the solution to the Schrodinger equation actually has in it the quantum numbers that you may already be familiar with, n, l, m sub l, and m sub s. Those quantum numbers come from the solution of the Schrodinger equation. So if you look here, if you look closely, there's n, there's l, where's m sub l? Somewhere else. Can't find it, but yeah, so that's where all of our quantum numbers are, right? The actual solution, the actual Schrodinger equation is not important here. That's not what you're being tested on. You are being tested on, do you know the rules for the quantum numbers that came out of it? I just want you to be aware of the mathematics behind how we actually got the quantum numbers, and the significance of them will relate to radial distribution functions, all right? So, okay, so these are the quantum numbers that come out. Here are the rules for our quantum numbers, all right? And we'll go through each of them. N, L, M sub L, M sub S. All of these quantum numbers, and do memorize this table, okay? Talk about, okay, how far away are you going to find that electron? What shape is the probability map that you're going to find it? And then what is its orientation? All of these numbers have significant meaning, and I'll try to relate it to a way that you can apply and determine where will you find that electron in a given place on our periodic table. All right, and so these quantum number symbols, represent this large delta X, this large probability of finding an electron somewhere in space. And again, the solution is not important. I just want you to impress your friends. If you're, watching a TV show and you see it on the background screen, and you can be like, oh, that's the Schrodinger equation, and you can impress people. But what's important here are the actual quantum numbers themselves. So let's look deeper into those. All right, so these are the main three. And we'll go through these main three, and then add a fourth quantum number at the end. So our quantum numbers are how we describe where to find an electron. So here are the main three. We have n, l, and m sub l. N, our principal quantum number, tells us about how far away you'll find our electron, so the size of this orbital. So an orbital is like a space you will find electrons. All right, and we see that n also relates to the energy of that orbital. All right, so size, so n is related to size and energy. N can be any integer value other than 0. All right, so n can be 1, 2, 3, etc. All right, so here we have an n equals 1 electron here. And then we have an n equals 2 electron up here. So we see n equals 2 is both higher in energy, but also the space that you'll find the electron is a larger space. So n is related to size and energy, right? And so if we think about where n equals 3 would be, n equals 3 is up here, so it's even higher in energy. And an n equals 3 electron is going to be overall even further away from our nucleus, the space to find it, right? So that is n, our principal quantum number, all right? So any positive integer other than 0. All right, so let's get into the next quantum number, and that is shape. So we see here, I talked about like n equals 1, 2, 3, and on the side here I have s orbitals drawn. They're just like these spheres. So the space that you'll find an electron changes with our L, our secondary quantum number here, L, right? So L identifies the subshell or the shape of your orbital that you'll find that electron. All right, so there are some shapes and letters you do need to memorize. So let's just go through the possible L's that we can have. So L can start at 0. So an L of 0 relates to what I call an S subshell. An S subshell is completely spherical. Completely spherical. And then L can increase from 0 with all of those integers. So we can have L of 0, we can have an L of 1. This relates to what we call a P subshell. A P subshell looks like a dumbbell. All right, and then we can have a D subshell. This is where L equals 2. D subshells look like butterflies. All right, so those L values actually have meanings. Remember, it's a solution to the Schrodinger equation. So these L values, these secondary quantum numbers, is actually the number of angular nodes inside that shape. Okay, so like what is an angular node? So my analogy for an angular node is, think about the L quantum number is like a balloon animal. Okay, you have a balloon. And so the L quantum number, the number of angular nodes, is how many times you need to twist the balloon to make that shape. So if you start with a balloon and L equals 0, you twist the balloon 0 times. So what shape do you end up with if your balloon is spherical? It's still a sphere. Great. So that's why an L equals 0 looks like a sphere, because you twist the balloon animal 0 times. What if L equals 1? What does that shape become? A dumbbell. Yeah, you twist it once, and now you have these 2 lobes that kind of come out, right? And that's where we get our P subshell, L equals 1. Right? And then L equals 2, that shape has 2 angular nodes. So how many times do you twist the balloon animal? Twice. So you take the balloon, you twist it once, it looks like a P orbital, then like fold it in half and then twist it again. All right, and that's how you get the butterfly shape. Though it's kind of wonky to think about that way. So twist it once, and then d orbitals, you twist it twice. So we see the number of lobes increase here. That an s orbital is completely spherical, a p orbital has 2 lobes, a d orbital has 4 lobes that come out. All right, so that's what those numbers mean. They do have meaning, all right? Okay, so those are the different shapes. Then as L increases, after D, we have an F orbital or F subshell, and then after that, the letter designations just change alphabetically. But I'll be honest that we don't really talk about F orbitals that much. We basically stop at D. That's what's important here. Okay, so those are the different shapes. But depending on the energy of your electron, so depending on the n value of your electron, you only have access to certain shapes. And so the rule is, given the energy level of your electron, so the n number, the possible L's are all of the integers between 0 and n minus 1. That's the rule. This is the rule. So that means if we have an n equals 4 electron, our possible L values are 0, 1, 2, and 3. So that's it. So the possible subshells we can have, L of 0 is an s orbital, so that would be 4s, 4p, because L of 1 is a p orbital. We can also have a 4d subshell, and we can also have a 4f subshell. Those are the possible subshells that we can have. 4 and n equals 4. And that will change for any other n value electron. Okay, and so each of those subshells have a specific shape based upon the number of angular nodes. Okay, so you see the combination of the n and l quantum numbers. I can combine these two things and specifically call out what subshell I'm talking about. So here, if I have an n equals 3 and an l equals 1, we can call this a 3p subshell. Just like I said, an n of 4 and an l of 0 is 4s. So we're basically telling the reader what is the n, what is the l in one swoop by saying 4s or whatever. All right? Okay, so let's do another example. So let's name all of the subshells that possess n equals 5. So if we go through the rules, if n equals 5, what is our possible L's we can have? 0, 1, 2, 3, 4. But let's actually specifically call out what subshells they are. So yes, those are the possible L's, but each of these L's have a specific subshell name. So an L of 0 is what kind of subshell? S, but we want to specifically call this a what S? 5S, because that's what the N is, so 5S. And so that means L of 1 is a 5P, then we get 5D, L of 3 is 5F, and then 4 is 5G. Yep, okay. All right, okay, another one. Why is there no such thing as a 2D subshell? So 2D, what's implied there is that the N value here is 2. So the possible L's in an N equals 2 are 0 and 1 only. So the only possible accessible subshells we can have for an N equals 2 electron is 2S and 2P. So that's why we cannot have a 2D, right? Because L of 2 is not accessible at that energy level, right? So that means, so what N level does D orbitals open up for us? 3. It opens up at 3. And that'll be useful for us in a little bit when we look at electron configurations. Okay. All right, so that's N, L, M sub L now talks about the orientation of an orbital within a subshell. So I mentioned before that, the L's are different shapes. S orbitals are a perfect sphere. P orbitals, on the other hand, are dumbbells, and we can actually orient them differently on an XYZ axis, all right? D orbitals also, because of their shape, they have unique ways we can orient them. So these orbitals, if we kind of look at this energy level diagram, one orbital, one ML value is one box on this picture. In each of these boxes, we can put 2 electrons. Right? So how we get from L to M sub L, this M sub L, this orientation, it's the number of boxes inside each subshell. So it's the number of orientations of that certain shape. And so the rule is, depending on what subshell you're in, will tell you how many orientations you can have. So the rule is, depending on what L you're in, the possible orientations are negative L to positive L, all the integers between it. So if we look at these examples, an L of 0 is an S subshell, right? So the only possible ML can be a 0, is the value 0. So in an S subshell, there is only one orientation. There's only one box. One orientation, one box. Each box can hold 2 electrons. So let's keep going. So L equals 1, this is a P subshell. So if we look at our ML rules, we can have -1, 0, +1. So there's 3 different MLs. So there's going to be 3 different boxes. 3 different boxes in our energy level diagram. So if there's 3 boxes and 2 electrons can fit in a box, how many electrons can fit in a P subshell? 6. Yep. Okay, great. So let's do the same thing with L equals 2. This is a D subshell. So let's actually get the numbers themselves. So ML can be -2, -1, 0, +1, +2. So how many boxes do I draw? 5, yes, 1, 2, 3, 4, 5. Look at the picture over here. How many different orientations are there? 5, yeah, so 5 boxes. So we can fit 2 electrons in each box, so a D subshell can hold 10 electrons. Okay, so each of these boxes are one of these orientations. 2 electrons can fit in each of these orientations. An orbital is a box. Depending on what subshell we're in, tells us how many boxes can be in each subshell. So you see here, all of these S orbitals have 1 box. All of these P orbitals have 3 boxes. This D orbital, or if we compared it to a 4D orbital, would have 5 boxes. Okay, so yeah, there's the general rule. There's always 2 L plus 1 orbitals in a subshell. That's how many boxes there are. That's how many boxes there are. All right, so how many orbitals, or essentially what I'm asking is how many boxes are you going to find in a 2S subshell? 1. And so what's the important number here? It's the S. The S is important. S implies L equals 1. Or no, 0, sorry. L equals 0. And that tells you the possible MS, the possible orientations. All right, how many orbitals in a 3s subshell? Also 1, yes, because again, it's the L of 0 that's important here. How many orbitals in a 2p? 3. Yes, because in a p, this is L equals 1. So our possible MLs are -1, 0, +1. So 3 boxes. And then how many boxes in a 3D? 5. Perfect. Okay. So we see that orientation is directly related to the shape that it is. All right. Okay, so let's go through everything and get what are the possible values of the quantum numbers for an n equals 3 electron or shell. So what are the possible boxes that we can write? So I like to just go through these. Okay, let's think about an n equals 3 electron. What are the possible L's that we can have for this electron? 0, 1, and 2. So we'll want to go through each of these shapes, each of them, and talk about identify what are the possible orientations we can have for each of them. So we got to do each of them. So for an L of 0, we call that an s orbital, right? What are the possible MS's for an L of 0? Just 0, that's it. Okay, and then if we move on to L of 1, because that's possible for this n equals 3 electron, L equals 1, we call this a p orbital. The possible, not MS, I meant ML, I'm sorry, ML. The possible orientations for a p orbital are going to be -1, 0, +1. That's where we get the 3 boxes for a p orbital. And then we do the same thing, L of 2. This is a d orbital. Possible orientations I can have are -2, -1, 0, +1, +2. All right? So each of these numbers within our MLs, that's an orbital. That tells me how many boxes I need in that subshell. So for a 3p subshell, it's just going to be 1 box. For a that's not 3p, sorry, that's 3s. Then for our 3p subshell, I'm going to draw 3 boxes because there's 3 different orientations, 3 different orbitals. And then for our 3d, we have 5 boxes because there's 5 different orientations. So how many total orbitals are there in a n equals 3 shell? 10. Yeah, count carefully. There's 9. There's 9, yes. So there are 9 boxes, 9 orbitals, 9 boxes within this n equals 3 subshell. 1 + 3 + 5 is 9, I think. Okay, so how many electrons can we fit in this n equals 3? 18. And what's the trick there? We know that we have 9 boxes. 2 electrons per box, so that means 18 electrons can fit within this shell. So 9 orbitals, right, times 2 electrons, per box, per orbital, and so that's 18 electrons. All right. Okay, and so I think I have like the kind of the tricks here. So in n equals 3, so for any n value, the number of orbitals, the number of boxes that you'll see will always be n squared within that shell. And then since 2 electrons in an orbital, double that number to get how many electrons you can fit in that subshell, in that shell, in that n value. All right, so those are our rules for the first 3 quantum numbers. So I didn't mention this, but I mentioned it that we can fit 2 electrons in each box. And the reason we can do that is because of the last quantum number, which is ms, our electron spin. So the only way we can put 2 electrons in a box is if one is spin up and one is spin down. That's the only way we can do it. So if our electron is spin up, we say that that has a positive 1/2 spin. And if it's spin down, we say it has a negative 1/2 spin. All right, so those are the quantum numbers for those individual electrons there. All right. So that's how we can put 2 electrons in a box. If we had both of them spin up this way, like yes, there's 2 electrons in that box, but those electrons would not exist in this manner because this does violate Pauli's exclusion principle, so we can't have that. All right, 2 electrons in a box, but only if they're spin up, spin down. Okay, so all right, so let's put it all together. Put it all together, all the rules together by looking at these examples and telling me, can you have an electron with these quantum numbers, all right? Is this combination of quantum numbers allowed? So I like to just go through them in order, like look at the n value, think about, okay, what are the possible L's I can have? Of that L, can I have the ML that's given? That's kind of the process I go through. So here, let's look at A. We have an n equals 2, so 3, and so I ask myself, what are the possible L's I can have for that n value? I can have 0, 1, or 2. So is that L value allowed? Yep, okay, cool. If I combine these 2 things, n and L, what subshell is that called? 3p, yes, because L of 1 is a p orbital. Okay, so then I can ask myself, in a 3p subshell, can I have an ML of -1 orientation? Yes, you can, because a 3p has 3 boxes, and one of them is a -1. So yeah, so we're just trying to put an electron right here, right? And then can we have a spin of 1/2? Yes, we can. Actually, yeah, that's what this is. So this is what that picture would look like. That's how we've located our electron. It's in a 3p subshell. It's in the orientation -1. Has a positive spin. All right, so this one is allowed. Yes. Okay, so let's look at the next one. Okay, n of 3 again. So our possible L's are the same, 0, 1, and 2. All right, L is 0 this time. So what subshell is this called? 3s. Okay, can a 3s have a orientation of -1? No, what should it be? 0, yeah, it should be 0. That's how we could make it correct. So this one is, B is not correct. Okay, next one. How many boxes would this 3s orbital have? Just 1, yeah, and so if it was correct with that 0, it would look like that. But that orientation is not -1. It has to be 0. All right. C. Okay. N of 2. So this sounds like it's the possible L's are 0 and 1. So we can have that L value. What is this subshell called? 2p. It's a 2p. So how many boxes does a p orbital have? 3. Can I have an orientation of 0 for this p subshell? Yes, I can. It's going to be like the middle one or something. Yeah, so that's okay. Yes, so those are okay. So can I have a spin of 0? No, the electron that I place has to be spin up or spin down. All right, so I can't have a spin of 0. So that one's incorrect because of the spin. All right, I could make it right by just making this a positive 1/2 or negative 1/2. Okay. All right, so next one, D. All right, so n equals 3. So our possible L values, L equals 0, 1, or 2. So what subshell am I talking about here? 3D. Yes, because L is 2. Can a 3D subshell have a orientation of 0? Yes, because a D subshell has how many boxes? 1, 2, 3, 4, 5. Yeah, so if we labeled these boxes -2, -1, 0, +1, +2, I'm just going to put an electron in this middle box. All right, and then is the spin okay? Yep. And so if I wanted to actually draw this, I would be putting an electron in that middle box, and it would be spin down, like that. Yep, and that's the electron that I'm talking about. So this is a 3D subshell. I'm putting it in that middle box, the orientation of 0. Okay. So D is correct. So so far only A and D have been correct. Okay. So E, N of, is that combination allowed? N of 1, L of 0. Yes, what is that called? 1s, okay. Can you have an ML of negative 1? No, there's only one box and it actually has to be 0, so E is not correct either. All right, so that's us using the quantum numbers, okay, and the rules within our quantum numbers. All right, so let's actually talk about what these numbers mean, because yes, you might just memorize, you know, the different rules relating N, L, M sub L, but these numbers actually have meaning. Remember, they're the solutions to the Schrodinger equation. We actually solve the Schrodinger equation in polar coordinates, and it actually tells us a little bit about where we find electron density relative to how far we are away from the nucleus. So usually in high school, when we talk about like S, P, and D orbitals, we look at contour models. All right, so we just say, oh, we have this spherical space, you'll find an electron. In a p orbital, it's in a dumbbell-shaped space, you'll find an electron, etc. But here, we're going to actually relate the quantum numbers to what we call radial probability functions. So this is us solving the Schrodinger equation for where to find a electron relative to the nucleus in radial coordinates. Okay, but we're never actually solving the Schrodinger equation. We're just thinking about how do these numbers relate to finding electron density. That's not just these shapes that most students know. We can actually use graphs to also represent where to find electrons. All right, so let's remind ourselves of the L quantum number, the shape one, right, where L is the number of twists in our balloon animal. But I mentioned before that that L quantum number is also the number of angular nodes in that orbital shape. So we know L of 0 is S, L of 1 is P, D, etc. So those shapes are actually related to the number of angular nodes in that shape. It's how many times we twist that balloon animal, right? So that's are the different shapes that we have. And then the number of different shapes within each of these subshells come from the possible ML values that we can have, right? So S orbitals have 1 box, P orbitals have 3 boxes, D orbitals have 5 boxes because there's 5 different possible shapes. All right, so but what I want you to get here is that depending on what orbital you're in, if I'm talking about like a 2s orbital, S means that L equals 1. So that S orbital has 0 angular nodes in that shape. That's what you need to know here, because it's going to be more useful for us. So that's how we know what that shape is, because that 0, that L of 0, comes from solving the Schrodinger equation, right? Okay, so that's the number of angular nodes within that shape. All right, so let's talk about S orbitals. So based upon I just said, S orbitals have how many angular nodes? 0, because L equals 0. Okay. Also in the textbook, sometimes they call angular nodes nodal planes. They're the same thing, right? Okay, so usually when we talk about electron shapes or where to find electrons, we show these contour models showing, hey, you can find this electron in this space. Another way we can talk about finding electron density is radial probability function graphs, where when the graph is high, here, these 3 different graphs, I'm just saying, hey, you're going to find a lot of you have a high probability of finding electron density here. Or in this graph, I'm saying, oh, you have a lot of probability finding it here, away from the nucleus, but not a lot here, and then a tiny bit here. Versus this one, it looks like you have probability of finding electron density in 3 different places, 1, 2, 3, but most of it's on the outside up here, all right? So and then another analogy I've used before is like if we're an atom and you guys are electrons, right? You guys are electrons, and the nucleus is like up here. You think about how this graph works. The x-axis is like me moving through the classroom like in this direction and trying to find electron density. You guys are the electrons. You're making my graph go up really high, all right? When I go all the way to the 2nd floor, I'll find more electron density up there. and a lot of electron density down here at this radius, but will I find electron density on the stairwell? No. So at that point, where will my graph be when I'm on the stairwell? It'll be 0. And so if you look at these graphs, there's a couple places where the graph goes to 0. There's certain places you will not find electrons, and that's when you're between energy levels, right? So mentioned before in the Bohr model, right? The only stable place your electron can be is on a energy level, that an electron cannot be between an energy level. And we see that in places where the radial distribution function goes to 0, where the probability of finding an electron is 0, right? So we call these points where the graph goes to 0, we call these radial nodes. Radial nodes, where the graph goes to 0, but you don't want to count the beginning or the end. You won't find electron density at the beginning of this graph because at a distance of 0, you're in the nucleus. So would you ever find electrons in the nucleus? No, you won't. So that's why the graph starts at 0. And then you also won't find electrons infinitely away from the atom as either. So that's why you don't want to count the beginning or end of the graph. You only want to count the middle sections where it goes to 0. So those are what we call radial nodes. So in this picture, this one, how many radial nodes are in this 1s orbital? 0. What about this 2s orbital? 1, yep. And then the 3s orbital over here? 2. It goes to twice. Okay, so yes, we got the number of radial nodes from the graph, but we can also actually calculate how many radial nodes should show up on a graph based upon this equation, all right? The number of radial nodes in a predicted graph is always going to be the n value minus the L value minus 1. So if we look at a 1s orbital, what is the n value in 1s? 1, and then what is the L value? 0, and then what is n minus L minus 1? 0, right? So based upon the subshell, given the n and L value, we can actually predict how many radial nodes are in the graph that you should draw, right? So we can do the same thing for a 2s orbital. The only difference is that n is now 2, L is still 0. So does this equation correctly predict the number of radial nodes? Yes, because it's 2 minus 0 minus 1 is 1. So a 2s orbital will have 1 radial node in its probability function. All right, and then the last one, 3s, n equals 3 here, L still equals 0. And so if you do n minus L minus 1, you again get the correct number of radial nodes that's drawn in this graph. It's 2, all right? And so just given the quantum numbers from the subshell designation, we can predict how many times your graph goes to 0. So, but this is like how I like to think of it. So let's look at the 3s graph, all right? So if you think of like, I don't know, like this 3s orbital like an onion, all right? Like an onion has layers. So on the outside, you have where you're going to find most of your electron density right here. This is kind of describing like that 3s layer. That's where you're going to find most of your electrons with that energy. But then you start working your way inside. All right, you might find a tiny bit of electron density in this 2s layer, right? That's what that middle hump is, while this tiny, tiny, tiny blip is that 1s layer, that you might find some electron density close to that nucleus with that same amount of energy. And so that's specific for a 3s, an electron with 3s subshell designation. So that's how I like to think about it, all right? Okay, but also, you know, just calculating the number of radial nodes will get you there too, where you do n minus L minus 1 to get that, where you only count the middle points where the graph goes to 0, because you can't have electron density between 2 energy levels. All right, so that's for an s orbital. Let's do the same thing for a p orbital. Okay, so p orbitals, here are contour plots. They look like our dumbbells, but we can also talk about radial nodes in p orbitals as well. So let's remind ourselves, how many angular nodes are in a p orbital? 1, because angular node means what? L. It means L. And that differs from radial nodes. Radial nodes is the n minus L minus 1 thing. So we've been talking about nodes, angular versus radial. Okay, so we see the shape here changes. It kind of looks like this dumbbell figure 8. Some students have the misconception electrons are like moving in this dumbbell shape or like in a figure 8 shape. They don't do that. Okay, they don't do that. They're not swapping from top to bottom either. I'm just trying to say you have an equal probability of finding an electron either above or below the axes here. That's all I'm trying to say. All right, that's not moving between both sides. All right, so p orbitals have 1 angular node. So that's the answer to this first one. There's 1 angular node because that's the L value. So if we look at this graph, how many radial nodes are present on this graph? 0. Okay, great. So if this graph is showing a p orbital, which p orbital is it? A 1p, a 2p, a 3p? Which one? 2p, yeah. Yeah, it is a 2p. So I'll show you, it's actually just some arithmetic to get that this is a 2p orbital. So let's remember our equation. The number of radial nodes in a graph is n minus L minus 1. I'm telling you this is a p orbital. So this is an n-p orbital. I just don't know what n is. I know it's a p orbital, but I don't know what n is. So you told me that this graph has 0 radial nodes. So 0. I'm solving for n. I don't know what n is. But do I know what L is? Yeah, it's 1, because I said it's a p orbital, minus 1. So you just do arithmetic and determine what does n have to be. N is equal to 2. In order to make all that work out. So we can write that this is a 2p orbital in this picture. And I mean, you can check your work at this point. 2p orbital, n equals 2, L equals 1. If you use the n minus L minus 1 equation, it's 2 minus 1 minus 1. There should be 0 radial nodes, and that's exactly what we see in this graph. So it's another, radial node type graph question, but it's asked a little bit differently in this example. Okay, all right. Okay, let's keep going. All right, so what comes after P? D. Okay, d orbitals have how many angular nodes? 2, because remember, angular nodes mean L. Okay, so the possible orientations we can have for a d orbital, there's 5 different ones. All right, so sometimes we use the ML designations to talk about d orbitals or p orbitals, but oftentimes what's more useful for us instead of like -2, -1 is actually to tell the reader exactly where along the axis your butterfly is lying. So for example here, d orbital along the YZ plane, I'm trying to tell you, hey, you have your butterfly lying across the YZ plane and it's being speared in the center by the x-axis, right? Or dxy, or no, what is this? dxz. So this orbital you see is lying on the xz plane and being speared in the middle by the y-axis, like a shish kebab. Right? Or here, this one's a little bit different. So 4 of the d orbitals look like butterflies, but the last one here is a little bit different. This is dz squared. dz squared kind of looks like a pz orbital, right? Where pz is, a dumbbell along the z-axis, but the difference is that a dz squared orbital has a belt around it. So that's the small difference. So don't confuse those two. D orbitals have belts around it. They are the xz squared designation, while pz is just saying you have a dumbbell lying along the z-axis, or the y-axis, or the x-axis. It's px, y, and z for those designations. Did I say that up here? Yes, so right here, px, y, and z, right? Is just what axes those dumbbells are laying across. Okay. So those are the different shapes. So let's go through angular node stuff. So how many angular nodes does a 4D orbital possess? 2, yes, because angular node just means L. Okay. let's draw the radial probability diagram for a 4D orbital. So really, I need to figure out, I'm going to draw a graph, and I need to figure out how many times it goes to 0. So I need to calculate how many radial nodes are present in this 4D subshell. So to do that, if I calculate what n is, and if I figure out what L is, then I can figure it out. So n is 4 in a 4D subshell. L is 2. So how many radial nodes are present? 1. Yep, so it's 4 minus 2 minus 1. So I'm going to have a graph that has 1 radial node. So how many humps will be on it? 2. Yes, because you do 1, 2. Whoops. And so only that middle one is a radial node. All right, so what I'm drawing in pink here, the 2 pink points, those are not radial nodes. That's just the beginning and end of your graph. The radial nodes are only in the middle, right? And so another way to think of this, like I said before, so here's the radial probability graph. There's wave function. This is their radius. The biggest hump here, this is, if you think of, again, an atom like an onion, the big hump on the outside, that's representing your 4D orbital in question. The little hump represents 3D. All right, if there was another little hump, that would represent 2D, but does 2D exist? No, it doesn't, so that's why there's not another little hump, right? So that's how I like to think of to help me visualize what these radial distribution functions look like. But for an electron with 4D energy, most of the time you're going to find electrons that far away from your atom, but you're not going to find electron density between these two energy levels. It has to be n equals 3 or 4 here. All right, so that's D. What comes next? F. Okay, so here you see there are 7 different F orientations, right? We could calculate that too, because in F, angular nodes is 3, right? That's our L value. So if we wanted to get the possible values of M sub L, they would be -3, -2, -1, 0, +1, +2, +3. So how many orientations did I draw? 7. So how many orientations are shown here? 7. Yeah, so there's 7 different ones. They are very complex. That's why they're not labeled any further. I just want to show you there are 7 different orientations because there are 7 different MLs. So there'll be 7 different boxes in a 4F orbital, right? Okay, so let's answer these questions because we can do that without like these actual orbital designations. How many angular nodes does a 4F orbital possess? 3, because that's the L value. Angular node is L. How many radial nodes does a 4F orbital possess? 0, yeah, because 4F, n equals 4, L equals 3. So n minus L minus 1, the number of radial nodes is 0. What about 5F? Number of radial nodes? 1. Okay, so n minus L minus 1. All right. Okay, so that's the meaning behind the quantum numbers. That's how we know the shapes. That's how we know where we will find electron density. They have meaning, all right? And it comes down to polar coordinates and finding electron density that way. Okay. So yeah, typical exam type problems would be like these ones, like how many radial nodes does a, I don't know, like 5s orbital have, and you just put in a number. Or I like questions like this one, like here, this is a d orbital. What d orbital is it? I like questions like that, where you're relating the idea of angular nodes, radial nodes to an actual graph. All right, that's the learning objective there. All right, and I would definitely say this idea, even if you took AP chemistry, you probably did not learn about this. Yes, and that's what makes college fun. All right, so those are radial nodes. Okay, so we talked about the 3 quantum numbers, N, L, M sub L, and then the fourth one is M sub S. That allowed us to put 2 electrons in a box, all right? Because we're one step closer to actually putting electrons in boxes, but we need to follow some rules. So if I give you energy levels, if I give you the number of electrons to place, you can place those electrons as long as you follow these rules. So the first rule is Aufbau's principle, which just means if given electrons, you always want to fill lower energy levels first before you fill higher energy levels. So like in practice, fill your 1s before you fill 2s, before you fill the next one. You just work your way from the bottom to the top. Okay, then the next rule is Pauli's exclusion principle, but that just says that no 2 electrons can have the same 4 quantum numbers. That's why we needed the MS quantum number that allowed us to put 2 electrons up and down in the same box, because if you have different spins, then you don't violate Pauli's exclusion principle. So the rule here is if you have to put 2 electrons in a box, they have to be spin up, spin down. They can't both be spin up, or they both can't be spin down, so you can't have this one. All right, and so the last rule, and this one's kind of the hardest, is if we start filling electrons in subshells that have multiple orbitals, so like P or D, for example, all right? So Hund's rule says that electrons are most stable when you maximize spin. All right, and so to maximize spin in practice, what you want to do is if you have multiple electrons to put in a P or a D orbital, you want to spread those electrons out, all right? Put them all in their own box before you have to start doubling up, all right? So for example, if we had to put 2 electrons in this P orbital, we're going to give each of those electrons their own box, and they're both going to be spin up here. Right? So if we put both of those electrons in the same box, this arrangement of electrons is actually less stable. So you're not going to see this in nature. Also, you don't want to put them in different boxes and have different spins, because this does not maximize spin. So this picture is also less stable. So you won't find this in nature. Okay, let me draw a different example. Does this picture violate Hund's rule? Does it violate Hund's rule? Is that allowed? Is that stable? Yes, it is. Yeah. So in this picture is actually on the same energy as the most stable one here. Both of these are equally as likely, right? For some reason, you know, as humans, we read, we write left to right, so we will put electrons in the boxes left to right, but you don't have to. You don't have to. So in this example, I still maximize spin. Electrons are still in their own box. So it still is okay with Hund's rule. What if I did this? What if I did this? Is that okay? It is okay, yeah. It is okay, because again, for some reason, our brains want to write them left to right, but you don't have to. And for some reason, we want to put the electrons spin up. But we don't have to. They can both be spin down. We still maximize spin in this case, but just in the other direction, all right? But I could make it wrong if I did something like this. If I did like this, like that would be wrong, because now I have not maximized spin in this case, all right? Or if I did like that would also be wrong, all right? Okay, so just make sure, like, you don't have to put them in left to right. You don't have to. And you don't have to make them all spin up. They could be all spin down and you could be fine. All right? Okay, it's just for some reason we like to do that because we read left to right. All right, so those are the rules. So let's go through the steps of placing our electrons. So here's our electron diagram. If I tell you, okay, fill in the energy level diagram for hydrogen, these are our boxes. We need to ask ourselves, how many electrons does a hydrogen atom have? 1. So that means we place 1 electron. Where is that 1 electron going to go? 1s, so it's going to be right there. And so we can write the electron configuration for this by telling the reader exactly what subshell and how many electrons are in that subshell. So for this example, the electron configuration of hydrogen is 1s, because that's the subshell, and then I put 1 electron in it, and that's it, 1s. And so the superscript is telling you how many electrons are in that subshell. Right. So that's hydrogen. That's hydrogen. So note here that all of the different subshells for n equals 1, 2, 3, see how they're all the same energy for a hydrogen atom? So that's only for a hydrogen atom. So if we go to the next slide, this is the electron configuration diagram for any element other than hydrogen. We see it kind of starts to split a little bit, right? So if you solve the Schrodinger equation for any other element other than hydrogen, we see the energy start to split. But we still follow the same rules, just using this diagram instead. So let's write the electron configuration for sodium. So we're going to do the same thing, place electrons, but we're just going to use this diagram instead. All right? And so the reason the diagram's different is because hydrogen only has 1 electron and 1 proton. Things get complicated when you add more electrons. So for sodium, how many electrons do we place? 11. So we just place 11 electrons following Aufbau's principle, Hund's rule, all that stuff. So the first electrons are going to go in our 1s. So spin up, spin down. Where do they go next? 2s. So spin up, spin down. Where do they go next? 2p. So the first electron goes here, and I want to maximize spin before I start filling up. So I'll go 1, 2, 3. And then 4, 5, 6. So I fill it up the whole way, but I still want to follow Hund's rule. All right. So I've placed 10 electrons, so the 11th electron goes right there, 3s. Okay. So that's how we filled the electron, the energy level diagram, but let's write the electron configuration. So telling the reader exactly where those electrons are. So it would be 1s. There's 2 electrons in the 1s subshell. There are 2 electrons in the 2s subshell. How many electrons are in the 2p? 6. And then 3s has 1. There we go. And so if you add up the superscripts here, you'll see they should add up to 11. Those are the 11 electrons. All right. So we can also write a shorthand way, all right, because there's we'll talk about atoms that are much heavier than this, so sometimes it's annoying to write all of them. Another way we can write this is if you look at the first 10 electrons, the nearest noble gas next before sodium is actually neon. So we can actually write neon in brackets. Writing neon in brackets, it's like a save point. It's like, oh, start at neon, and then we can just move, and that takes care of 10 electrons. Just write that 11th electron for sodium. So we can write neon to take care of those first 10, and then we just have to write 3s1 for sodium. But do recognize that you still have to write the right n value, and I have some tips on how we do that. Okay, so we use this diagram for almost every other element other than hydrogen. Do you need to memorize this? No, all this information comes where? From the periodic table, yes. And so this is how I use the periodic table for electron configurations. I memorize 3 things. Hydrogen starts 1s. Boron starts 2p, because does 1p exist? No, 1p does not exist. Scantium starts 3d. That's all I memorize. Because I should know if scantium starts 3d, then this element is what? 4d. This element is 5d. Or boron here is 2p. That means the element under it starts 3p, 4p, etc. Right? So we see here our alkaline earth metals. That's our S block. Our elements on the right side, this is our P block, and then our transition metals, those are our D block elements. All right? So to write electron configurations, we don't actually have to fill the diagram like this. We can just think, okay, where are our electrons going to go until we get to that number of electrons for this atom. So for example, lithium has 3 electrons, right? So we locate where lithium is on this periodic table. It's right there. And so we just work our way up from hydrogen to get to lithium. We place electrons, 2 of them in the S, 1s, and then 1 of them in the 2s to get there. Those are our 3 electrons. We can do the same thing with oxygen. Let's just write, where is oxygen? It's like right there, I think. And so we start at hydrogen and we just work our way up. So oxygen will fill up our 1s subshell first. All right, that brings us here to lithium. So lithium starts 2s, so 2s, we want to fill it up the whole way. That brings us to boron, and then this helps with, if you remember, boron starts 2p because 1p doesn't exist. So 2p, but how many electrons are we going to put on our 2p? 4, yeah, look at the periodic table. All right, so we can do the same thing for potassium, all right? So we would do 1s2, 2s2. We're going to fill up that 2p, so 2p6. Okay, we need to keep going. So 2p6 will bring us to sodium, so 3s2. So sodium is 3s. If you ever forget, you can go back to hydrogen and be like, oh, hydrogen is 1s, lithium's 2s, sodium's 3s. Then we're going to fill up our 3p all the way to 6. That brings us to argon, and then potassium is 1 more. That starts 4s. We'll put 1 electron there. All right, that was a lot of writing, so I want to use a save point instead. Where's my save point on the periodic table? Argon, yeah, so argon will take care of a bunch of electrons. How many? 18. So I can just write argon 4s1. And so that's useful understanding like, oh, hydrogen starts 1s, because then you can just count down. If you're starting at argon, you need to know, okay, what is the N value in potassium? And so you can just count your way back from hydrogen. Hydrogen is 1s, lithium's 2s, sodium is 3s, potassium would be 4s. All right, so that is our shorthand. Let's do shorthand for zinc. So zinc's closest neighbor is argon again. So we're going to do argon, that's my save point. From argon, I'm going to fill up the 4s. And so what subshell is zinc in? I'm going to fill up that next subshell, but what subshell do we call that? 3D. We know it's a D subshell, but D start at 3, so that's why I memorized scantium starts 3D. And that is like something that kind of just has to be memorized, so that's 3D10. Okay, because 10 electrons brings us all the way to zinc. All right, germanium. It's in that same row, but it's a little bit weird. So argon is still my save point. I'm going to fill up that 4s again. I'm going to fill up the D subshell, but it's 3D, remember. So once I get to zinc, to get to gallium, what new subshell am I opening up? It's a P subshell, but which one? 4, yeah. So again, if you forget, boron is 2p. Aluminum is 3p, gallium is 4p. That's how I remember it. So I don't have to start all the way at the beginning. That's annoying. So this is 4p. How many electrons? 2. All right. All right, so that is electron configurations. All right. So let's look at some anomalous electron configurations. So we just did most of the predictable ones. There's a couple of anomalous electron configurations, just meaning like the work we just did doesn't work for some of the elements. And those elements are chromium and molybdenum, and then copper, silver, and gold. So these are our D4 elements and D9 elements. There's some weird stuff that happens when we're just on the cusp of half-filled and fully filled D subshells. All right, so what we see is there is enhanced stability when we completely fill a subshell, so this would be like D10, or if we exactly half fill a subshell, so like D5. So for example, chromium has 24 electrons. So you would expect, if we did like our work like we did before, chromium would be S2, D4. But we don't actually see this in nature. What we see instead is one of those S electrons jumps ship so we can half fill a D shell because it's extra stable. You get a little extra stability when you half fill something. So now we actually have two half fills subshells. So instead we see S1D5. So we just rearranged our electrons to just be a little bit more stable. And so that happens for chromium and molybdenum, but not tungsten. All right, and so that's our D4 example. So we see something very similar for copper, which is D9. If we did our work, we would see that copper is S2D9, but like the D subshell is like 90% of the way filled. So why not just like completely fill it? Consolidate your electrons in like a bigger cup. And so what you'll see actually is one of those electrons jump ship over there. And so what you actually find for copper, silver, and gold is S1D10, right? So do memorize these. Memorize these. You just have one S electron jump ship, so you can have either half-filled or fully filled subshell. And this is important when we do valence electrons and unpaired electrons and stuff. Okay. So those are our anomalous electron configurations, so ones that don't fit our, our work perfectly. Okay, so remember, we can represent electrons in these boxes. So other ways we can talk about electrons in boxes is to count the number of unpaired electrons in our electron diagram. So for example, here's lithium, has 3 electrons, where we put the first electrons in this box and the last one over here. So I could ask like, how many unpaired electrons are on lithium? And so these 1s electrons, these are paired, while 2s, these are unpaired, or that one's unpaired. So lithium has 1 unpaired electron, 1 electron. Because remember, can we ask you to draw these diagrams on an exam? No. But we could ask it this way. Okay, I could ask you how many unpaired electrons are on a fluorine atom, because that assumes you know the electron configuration, you can draw the correct electron diagram. So that's how we get around having you actually draw a diagram. If we ask you how many unpaired electrons are present, because it means you have to follow Hund's rule and all those things. All right, so that's the way we get around it. So let's do this. How many unpaired electrons are on a nitrogen atom? So let's write the electron configuration. So it's, I'll write the whole thing. So we have 1s2, 2s2, 2p, how many electrons for nitrogen? 3, okay. And so we can draw that. So 1, that's my 1s, there's my 2s, and then there is my 2p. All right, and so we're going to draw in those electrons following Hund's and Aufbau's principle. So 1, 2, 3, 4, 5, 6, 7. There we go. Okay, so how many unpaired electrons are on nitrogen? 3. So that means you have to draw it correctly and do the electron configuration correctly. All right. Here's another way to ask it. Identify the neutral elements that have 2 unpaired electrons in their 4p subshell. So 4p has 3 boxes, right? So if I have 2 unpaired electrons, how many electrons should be in this subshell? 2, yeah, so 1, 2. Okay, so it looks like this is a 4p element with 2 electrons in it. What element is that? If you look at the periodic table, what 4p element has 2 unpaired two electrons? Wait, 2, 3, wait, which one? Germanium, right? So if this is 4p, so boron's 2p, aluminum's 3p, gallium's 4p, so this would be germanium. All right. Is there another way we can have 2 unpaired electrons? Yes. With how many electrons in the 4p? 4, yeah, so another way we can draw it is 1, 2, 3, 4 electrons. All right, so that's another way we can have 2 unpaired. So this would be 4p4. What element is that? Selenium. All right. So note here with these last examples, we didn't have to write out the full electron configuration here. All right, we actually only looked at the valence electrons. We didn't actually have to look at the whole deal. And we'll talk about valence electrons. I have, 5 minutes. So we can talk about valence electrons, but before we do that, let's look at these examples. Sometimes drawing the correct diagram can be a lot easier than looking at these diagrams and figuring out why are these wrong, right? So let's go through these. Is this diagram A, is this correct? No, but why is it incorrect? Which rule does it violate? Hund's rule, yeah, because we want this electron to be over here and spin up, so we would have to change its ML and its MS to make it fixed. So this A violates Hund's rule. What about B? Is B correct? No. What's wrong with it? It violates which rule? And this is the hard part. Like, yeah, I know it's wrong, but why is it wrong? Which rule? Pauli's, yep. And so how could we change a quantum number to make this right? How would you change it? You would take this electron and flip it, right? So what quantum number are you changing? MS, that's how you change it. All right, what about C? Is that one right? Nope. So this one violates Aufbau's principle. I want to move that electron over there because we didn't fill from the bottom up. So this one I would change the N value to make it correct. All right, is D correct? Yes, it is. Even though the electron's in the middle, it's correct. All right, even though it's in the middle. You don't have to put electrons left to right. What element is this? Is it boron? Boron, okay. What about E? Is E correct? Yes, it is correct. You don't have to start your electron spin up. They don't have to. Or left to right. So what element's this? Carbon. Okay, so those ones are correct. Okay, so we got 4 minutes. I want to finish this chapter because I want homework to be due before the exam. Don't blame me. And that's the idea of valence electrons, okay? I have to test you on it anyway, okay? Valence electrons, so all chemical reactivity happens from the outermost electrons on an atom. And so to figure out how many valence electrons are on an atom depend on where it is on the periodic table, and it depends on what we see in nature, all right? So for example, if this was chapter 2 and I asked you what's the charge of a sodium ion, what would you say? Sodium, Na. +1. So sodium loses how many electrons? 1. And so what we see is sodium has 1 valence electron, an electron that is very easily lost. So the first rule for valence electrons is for main group elements. So these are S and P group elements. These ones are easy to predict valence electrons. It's just its group number. Where things get gross and strange is, of course, transition metals. Transition metals have variable valence electrons, and so basically if you are early in the D block, count all S and D electrons. Okay, so like all the elements up to manganese. If you're later in the D block, only count S electrons. That's the rule, and that's explained down here also, right? And the reason is because of observations. Don't get all like tied up on the details. Usually these middle ones aren't asked. So for example, like manganese here. So for manganese, we actually want to count all of the electrons on the outermost shell. So it's going to be 1, 2, 3, 4, 5, 6, 7 valence electrons on manganese. The reason I know there's 7 valence electrons on manganese is because manganese +7 exists. That's why I know. Versus like zinc, I know that it only has 2 valence electrons because zinc only forms +2 ions. And so it has to do with the observations. All right, so easy ones are S and P block. It gets a little bit spicy with D block elements. So we got 2 minutes. Let's do valence electrons for these elements. So there's 2 ways you can do it. Either write out the full electron configuration or just look at where it is on the periodic table. What do you want to do? Just look at it, yes. So let's do the easy ones first. Sodium, how many valence electrons? 1, because it is a 1A. It's a main group element. Sulfur, 6, because it's 6A. I'm going to skip these ones. Bromine, 7, because it is 7A. Oxygen, 6. Carbon, 4. Silicon, also 4. I'm going to skip those 2. Magnesium, 2. Okay, this one's tricky. Neon. It's not 0. It's 8. Remember, it's the outermost. Okay, so even, yes, okay. So let's do the tough ones. Titanium is right here. So I would call that an early transition metal. So how many valence electrons? 4. And it is 4 because titanium 4+ exists, right? Zinc is over here. I would call that later transition metal. So zinc actually only has 2 valence electrons here. And the reason I'll write it out, zinc is 4s2, 3d10. And so those d10 electrons, they're just so low in energy, they'll never get lost. But those 4s electrons will. Okay? Versus titanium is 4s2, 3d2. These electrons are more similar in energy, so all of them can be lost. And that's the real reason. All right. Silver has 1 valence electron because this is an anomaly. It's 5s1, 4d10. All right, because it's one of our anomalous electron configurations. Also, only silver plus 1 exists. That's why it's 1 valence electron. Manganese has 7 valence electrons because it is 4s2, 3d5. All right, and again, because we know manganese plus 7 exists. That's the real reason behind those rules. All right, so online homework is due. I mean, you're going to be tested on it on Tuesday anyway. All right, I still have office hours right now. Remember, your last day for the mid-semester SCI is tomorrow. Your exam is Tuesday next week. My review session is on Sunday. Have a great break.